It is a pleasure to introduce Miles Cranmer today, an assistant professor in data-intensive science at the University of Cambridge, jointly appointed between the Department of Applied Mathematics and Theoretical Physics and the Institute of Astronomy. He received his PhD from Princeton University with time at Google DeepMind and the Flatiron Institute, and before that earned his bachelor's from McGill University. Miles' research focuses on using machine learning to help automate scientific discovery in the physical sciences, asking in part what it would take to build models that don't solve just one problem, but generalize across many. Today, he'll be telling us about polymathic AI, an effort to build general-purpose AI systems that can learn and reason across the physical sciences. So please join me in welcoming Miles Cranmer.
All right. Yeah, thanks for having me. So today I want to talk about this idea called a foundation model, and specifically in the context of science, astronomy. So I want to motivate this with kind of a comparison between physics and machine learning. Physics seems to have this weirdly powerful generalization property. General relativity published in 1915, but it's still accurate. But basic machine learning models, they struggle a lot, even a little bit outside of their training data. So why is physics so much better at generalizing? I think this is a really important question to answer, and it's really interesting as well. I'll give you my opinion. You might disagree with me, that's fine. My opinion is I think this is because, and I'll kind of say what this means. I think it's because physics reuses models, it reuses ideas. But in machine learning, whenever you build a machine learning model, you start from scratch. Every time you build a new machine learning model, you randomly initialize all the parameters and you train it from scratch. Whereas in physics, you need to have your new model satisfy all existing observations, and kind of obey the principles that you've kind of defined. So when a physicist writes down the model, they use mathematical operators. And so I'm going to get into this a bit. I think these operators are kind of, well, I don't want to maybe spoil it. I'll get into this a bit later. But actually, let me skip this. So I want to make a I guess kind of a provocative statement. I think the concept of simplicity is kind of poorly worded. I think the way that we kind of say something is complex or simple in science is kind of, it's a good metric, but I don't think it's kind of the right language when we talk about complexity. And I think Occam's razor kind of misses the actual point. I'm just going to go on a philosophical ramble here, just to let you know. So I think when we refer to something as simple, what we actually mean is it's reusing pieces from other models that have been proven useful. So let me ask you, do you think x plus y is simple? Would people consider like 1 plus 2? Is that simple to you? I think most people would say yes. And then if you get into why is 1 plus 2 simple? If you really think about why that's simple, it's actually like there's not really any reason it should be simple other than it's familiar to you, and it's familiar to you because it's useful. So in the history of science, we've found different concepts that are useful, and we get familiar with those concepts, and they become simple to us. So simplicity is kind of like, it's almost like a human psychological thing. The reason addition is simple is because it is so broadly useful. I think this is the kind of right framing for it. I mean, even some animals know how to count. Like bees can count up to 4, for example. And I think the really interesting thing is that in our universe, if some kind of concept or model or operator is useful for problems A, B, and C, it seems it's likely to also be useful for a new problem D. And so you get this kind of compositionality thing where you can combine operators, build hierarchical models. So I think we can use this to kind of rephrase Occam's razor. Instead of saying simple models are more likely to be true, I don't disagree with this. I just think the wording of simplicity is wrong. I think what's actually happening is that useful models are useful. Useful models get reused. The models that survive aren't the simplest. They're the ones that keep working, and we kind of get familiar with them, and so we call them simple. So simplicity as a concept is just kind of a descriptor based on human psychology and what things we are familiar with, but I wouldn't consider it real. Okay, now back to machine learning. Specialist machine learning, so this is like not language models, not these kind of large chatbots. This is like traditional machine learning, like line of best fit, random forest. Machine learning can do very silly things. So if you have a data set with like something weird in it, a neural network will pick up on everything you give it. So there was this classic example of neural networks trained for detecting pneumonia in hospital patients. And it was later discovered, like they had this splashy paper, and like machine learning is very good at detecting pneumonia in X-rays. And then you look at what the model's actually looking at. It's reading this token in the background of the X-ray that basically says if they're in the pneumonia ward of the hospital, right? Like they'll pick up on everything in the data set. They don't really have common sense. They don't have, they'll just kind of memorize the artifacts in your data. So this is problematic. Now, one of the ways that I think this has started to be addressed is this shift in machine learning to favor pre-trained foundation models. So foundation model, the most common examples like ChatGPT. ChatGPT is a foundation model for language. It's one model that was pre-trained on tons of different text, and then it was fine-tuned to be a chatbot and be nice to you. And this is kind of how it works. In a foundation model approach, so rather than just taking a machine learning model that is like a baby, it has no understanding of the world, and you just show it examples. In a foundation model approach, you gather tons of diverse data, and you train a very general model on all of that data, and then you do this fine-tuning stage, also called post-training, where you adapt it to a specific task. So this is kind of the foundation model approach to doing things. In a language model setting, this would be like training your GPT model on like all the text images on the internet, and then you fine-tune it to follow instructions from a user and like not swear at them or whatever, because the internet has tons of that, right? So this approach seems to be very powerful, at least for language, because this language model, because it's seen so many different things, it learns these very general concepts internally. Like it has these very powerful features internally. So when it adapts to a new task, it needs less data because it already has these very general concepts. And this is why language models, like they're very good at basically generalizing, right? Like they've never seen that specific sequence of text that you type into them, but they can kind of adapt to it. So why would you want to do that practically? So the main thing is you just get this universal improvement in prediction accuracy, like language models that are pre-trained on vast text and then kind of further tuned on chatting with users, they just work way better. The downside is you have this big upfront training cost, but every other task, you need less data, less compute, And so there's many advantages from this. Okay, so I talked earlier about this kind of this simplicity. Simplicity is like it's actually just utility, and so shared concepts are kind of the underlying structure. I think this is partly why language models work, is because one language model that has been trained on, like French and Spanish, it needs less data to learn Italian because there's shared concepts and there's shared grammatical structures and words. And so by showing the data, tons and tons of diverse examples, you're kind of giving the model this general grammatical understanding before you teach it, a specific task. I think there's something similar in science. So in maybe language, you have shared grammatical structures, shared like concepts. In science, you could think about this in terms of like universality classes, like causality is relevant for tons of different sciences, measurement, modeling. You kind of zoom in, maybe conservation laws are relevant for many different problems, multi-scale physics. And so science also has this, right? There's also these shared concepts across science that we could exploit if we had foundation models. And so this is where we started this collaboration called Polymathic AI. So this is a research collaboration. A lot of people think it's a startup. It's not. It's a research collaboration. So there's a big team at Flatiron Institute, NYU, and then my group at Cambridge. And basically we have, so a lot of the, our models are trained on massive amounts of compute and then released open source. And so really we started this to kind of really push this concept of foundation model forward for science, because I think it's a really powerful idea. Okay, so a bit of history. 2023 was when we started, and we started out doing kind of prototyping models. So this is one of the first models we released called multiple physics pre-training. It's a similar idea to foundation models in general. You have different physical systems. I forget what PDs these are. They're all like fluids. You train this tokenizer. So it basically you could think of it as like collapsing these fields into this higher dimensional space where you then do this like universal PD solver. So this is kind of like, okay, you've got maybe 10 different physics. You map all of those 10 physics to this higher dimensional space, and then you can do your universal PD solver. Basically, it is learning to predict the next step in a simulation, in a physics simulation. And it learns this on many different physical systems with the idea that if it can do that well, maybe it's picked up general concepts that it can exploit. So one example is advection diffusion. You train the model on advection, you train it on diffusion separately, then you need much less data to adapt to advection diffusion because it's already seen components of the dynamics. And you can see this very clearly if you have a model that's trained from scratch, which by the way is how we currently do machine learning for science. You can see it needs much more data to get to a similar performance as the pre-trained model. So even though the pre-trained model, it hasn't seen that specific physics, it's seen the pieces of it, so it kind of has a general idea. This is something that, so one of the things people ask us is like, okay, well, how close does the physics need to be for me to get something out of it? Like, how do I have to have a bunch of different special cases of Navier-Stokes to get generalization in like fluids. So we ran this experiment thinking it would immediately not work. And then we were surprised it did work. What you're seeing here is the top line. This is a model that has been trained from scratch on like 200 data points up to 800 data points. So it has the worst performance. The one at the bottom, this has been trained on related physical systems. So it's like other PDEs that might be in a similar domain, but they're not exactly the same PDE. The middle one is cat videos. So even pre-training this model, so it's basically like a video prediction model. It's predicting the next frame of a video. And so this is a video foundation model that has been pre-trained on stuff like cat videos. And even that helps. And so this kind of went viral on Twitter at the time, because it's like, you train a model on cat videos and you get this state-of-the-art turbulence prediction model. I mean, I think it's, yeah. Yes.
But is your AI model actually working with PDEs, or it's some
working with
generalized representation?
Sorry, what was the second part?
Yeah, how is it representing the PDEs?
So they're represented, we get the solutions to the PDE. It's not symbolic.
It's not symbolic.
So you don't even tell it the PDE. You just give it data
Okay.
that you've generated either from an experiment or DNS or something. And you basically feed it in as frames, like time steps of different physical fields.
So why go through theory at all? Just give it experimental data as much as we have and get more data, and that's it?
Yeah, I like how you think, yeah. Yeah, I mean, this is what people do in weather, for example. Like AI weather models, they're better than the best numerical weather models now because they just train on data directly. And the data, like the experimental data, is, of course, it has all the physics that we're not taking into account in the simulation. So AI weather models are now superior to numerical. So this was the kind of the physics model. We also had this paper, AstroClip, where this is basically like it's a model that is trained to map images to vectors and spectra to vectors, and then you basically try to pull those together in this neural network space, and you do this for many examples, and this model gets very good at basically mapping from images to physical properties, because it knows, like, okay, this is like for this specific galaxy type, it maps to this feature vector, and then I can map that to physical properties. So this was like another prototype paper. There's also been like other work in this space. So this is Zubot 2023, which is kind of like a multitask supervised pre-training. This is another contrastive example from another group. And this is AstroPT from Smith et al. So there's other examples kind of in this space as well. So this was kind of like the year that we were figuring out like what we want to do. And we realized one of the main challenges is this data set. Like we need to aggregate high quality data. We need to get it into a uniform format. So 2024 was mostly data set formatting. So with two collaborations, we released these two data sets. We released this data set called The Well, which is 16 different PDEs. So many of them are special cases of Navier-Stokes, but they do span, so some of them are like active matter, reaction diffusion, so it's many different PDEs. And then multimodal universe is literally just like astro data from surveys, just put into a uniform format cross-matched. And so, yeah, so multimodal universe involves some people from the CFA too. So these were the papers, multimodal universe in the well. They make it, basically it makes it much easier to train this type of model on data. Okay. So the well, if you're interested, so this is, it's been actually used by other people to build physics foundation models before we actually released our model, which was cool. It's this nicely formatted data set for building these types of systems. Again, we give you the PDE, but the data that you train on is the actual numerical simulation. Okay, so that was 2024. 2025 is when we really started to scale up and try to push this to like actual large-scale foundation models. So one of these is called Walrus, which was Mike's idea. I like it. I like the name Walrus. It's unique. I don't know. So this is Walrus. It is. These models are like really expensive, so they're trained on like 100 GPUs for a week, like all together at once. The model architecture, so it's a similar idea in that you have like different time steps on a discretized grid. So you represent like density, velocity, temperature, and you give it maybe 3 time steps over a box. You could either have a 2D or a 3D physics. You pass in this hypercube of numerical data into this foundation model, and it goes through all of these steps, and it basically spits out, this is my best guess for the next step. Walrus itself, it's similar to video foundation models where you give it the previous frames and it tries to predict the next step. Like if you've ever generated some AI video, they use probably similar concepts internally, but it's basically that applied to physics data. I won't get into that maybe. This is kind of what it looks like. So these are some of the different systems. This is like the Rayleigh-Taylor instability. I think this is MHD data. This is the Euler data set. Let me see. I think this is reaction diffusion. So basically tons of different PDEs, and it's one model. So internally, it's kind of learned this general solver for physical systems. Now it's only been trained on simulations. So ideally, you would tune this to experiments. So I'll talk about that later. Yeah. Learn the next step. Yeah. Any other questions?
How do you ask questions to a model like this? I mean, what kind of questions can you ask? I mean, as Avi pointed out before, maybe we don't need the theory at all, we just need data. So in which way is it that we're supposed to ask questions to a system like that on a new physical system?
So these models, they are very inflexible in terms of, I guess, like task. So this model is like one task, but many physics. The one task is give me the next step, and that's all it does. Now, I think in the future, it would be nice to have physics foundation models that you can query with language, for example, or maybe like, oh, here's the first step and the final step, what's the PDE or something. So I think long term, it would be nice if you could ask them many different questions. Another thing is that for these types of models, you do want to train them anyways. Like if you have a physical system and you have data from that, you want to train the model just like any other machine learning model. Because I think in, two groups could simulate the same physics and get different results because of the choices they made numerically, right? So I don't think there's going to be a model, like a physics foundation model, that will just work out of the box on any system. Like I think you're always going to have that fine tuning, but it's a foundation model in that it gives you a foundation to train your downstream model from. Makes sense. Yeah, I'm happy to take questions throughout if anybody has others. Okay. So we train this model. We've fine-tuned it for different tasks. So these are some of the tasks. So I think this is Yanfei Zhang's red supergiant convective envelope. I think this one has like only 3 simulations in total, and they're really, really expensive to generate. But the advantage of using this model is that it doesn't need more than 3. Like 3 simulations is enough because it already understands physics. So it can adapt very easily to this type of simulation and then generate more. So Rayleigh Taylor instability is another one. That one's really hard. Yeah, so the detailed results are in the paper. The other model, so this is called ION. It's an omnimodal foundation model for astronomy. This is the team behind it. In this model, you basically want to learn, a mapping from any type of astronomical data to any other type of data for the same source. So to assemble the data set, we have these different cross-match surveys, and the model essentially learns to go from one to any other. And by doing that, it kind of learns general astronomical principles. So this is essentially how it looks in practice. So if I give it, an image to my model, I mask part of it. So I mask some of the pixels. I hide these pixels from it, and then I ask it to fill in those pixels. I say, okay, what's here? What's here? I do the same for spectra. I hide part of the spectra. I ask it to fill it in. Physical parameters, segmentation maps. So there's many different modalities. So like a spectra and an image, those are 2 modalities. And it also does this with multiple modalities at once. So you give it a spectra and half the image, and then it fills in the other half of the image. So it learns like all of these different directions simultaneously, which basically gives it this strong, it learns the distribution of data, like the full joint distribution of data. And this is very powerful for downstream tasks. So more specifically, ION is a transformer encoder-decoder. So this is kind of the original transformer architecture. The way it works is that for each modality, like you have an image modality, spectra modality, you train what's called a tokenizer. So I guess one way to explain this is when you talk to a language model, they need to convert the text into numbers. The way they do that is they have this dictionary of mappings from word to vector. So every word that you might type, or character, or symbol, they map that into a vector. Okay, and they've trained these vectors to kind of represent things. So we do the same for astronomy data. So for images, you train this tokenizer to go from an image to a sequence of vectors, or from a spectra to a sequence of vectors, from a segmentation map, from physical parameters, from many other, so it's in total 39 different tokenizers representing all the different surveys and types of data. So you give me any data in astronomy, and I'll give you a sequence of vectors. I'll give you the sequence of vectors that is basically like my model's language. So my model speaks in these sequences of vectors. To train this model, I give it a random set of those vectors, and I ask for the other ones. So it's like, okay, I gave you, these 4 modalities. I gave you this part of the spectra. I gave you this part of the image. Give me the other ones. And the model learns to predict the other ones based on the data that it does have. So this is kind of, I think, Raphael, to your point, this is kind of like, it does enable that flexibility, because now you can ask different questions. You can give it an image and ask for a spectra, because you basically say, I want you to predict these types of tokens, and it will give you a spectra, or give me an image or something. And so you train this for random subsets of these vectors, just on all the data we can get. And it learns these very good representations internally for astronomical data. And so as a demonstration of this, so this is the prediction accuracy for galaxy properties, so kind of held out galaxy properties, comparing standard machine learning approaches with the pre-trained models. And so you see, like, for 100 data points, standard machine learning is terrible. Like, it doesn't know anything. It has to learn everything from scratch. It's just hard. It's just a harder problem. But you take a pre-trained model, and you train that on the 100 data points, and it does much better. So at the data poor regime, like you only have 10 objects of a given type, it gives you much better performance for that. But also, even at the data-rich regime, it makes the model more robust, because it kind of has these general, like these very reasonable physical features internally. Just like how language models, like they have good features internally for representing grammatical structure or concepts. They're not just like learning it to talk to a user, they're learning it for like every context. So it's kind of similar, but for astronomy. Yeah.
How critical is like attention and these vision transformers to the performance of the model? Would this be totally hopeless with fully convolutional models?
So
Do you have a sense for like, is the alpha as big as it is for language models?
So the tokenizer actually does have convolutions. So those are where each modality will have a different type of tokenizer. So if you have like tabular data, it might be like a multi-layer perceptron. But if you have an image data, you might use a CNN, for example. But once you've assembled this sequence of vectors, you just give it to a transformer that looks like a language model, for example. And this is similar to how some language models work with image data. Like when you paste an image into ChatGPT, it kind of has similar concepts. Like it'll embed those images into a sequence of vectors, and it's basically like the model's language. So it's similar for here, except we don't have any language here. I mean, this is something that keeps coming up, is like, should we teach our model like how to talk? I don't know. Like I feel like that is something that industry is going to just do way better than us. So we'll stick to the stuff that doesn't make money. I don't know. Yeah. Yeah. Yes.
Can you ask this model so why it makes it better? So what does it learn from about the problem? So does it learn the physical laws that go into, I don't know, maybe this one or the one that you showed before, training simulation. So does it learn, I don't know, conservation laws or something like this?
Yeah, great question. So we are currently interrogating the Astra model. We have interrogated the physics model, so I'll show some of that a bit later. But it does seem to kind of have physical features, which is interesting. Oh yeah, okay, now I'm actually, yeah, I've got the slides. Okay, so what has it learned? Like we've said, it's gonna learn more physical features because it's seen so much data. Does it? So one thing that people will say is like, oh, it's this very large model, so it's more opaque. Actually, no. I think that, it's still a black box relative to physics models, but I think it's actually more interpretable than small specialist machine learning models because it learns better features, as I will show you. So it's actually, in a sense, like it's more interpretable because it just understands the physics better. Whereas like normal machine learning is just doing like lookup tables and interpolating. So this is work led by Rio, my student, on understanding walrus model. What we wanted to understand is, so there's some of the data sets have vortex, and some of them do not. How does the model represent this internally? Like, how does the model see a vortex? And if we understand how, can we kind of like reverse engineer it and manipulate the model and basically like alter those physical features? So the way we do this is called, it's called activation steering. It's been done for many years in the vision literature, computer vision. So we adapt it in a physics context. The idea is that you have this data set where you have this feature F, like a physics concept, turned on. So in this setting, it would be like this data set has vortices. Then you assemble this other data set that does not have that feature. So this is the data set of laminar flows. This has no vortex. Okay, so you've got this data set where it does have a vortex, data set where it doesn't. Then what you do is you basically like, it's almost like you measure the neurons inside the model. So they're called activations. It's like you're measuring the neuron pulses when it looks at a vortex and when it's not looking at a vortex. These can be represented as large vectors. So you've got one vector every time you pass data into the model. You've got this big vector. All you do is you compute the difference between the average vector when it does have a vortex versus when it doesn't. Okay, so it's basically like you measure all the neurons when it's looking at a vortex, measure the neurons when it's not looking at a vortex, compute the numerical delta between those. This gives you basically like a direction that represents the concept. So it's a concept direction in the model's like neural state, essentially. Then you can steer the model along that direction. So you've measured this delta, which corresponds to the difference in like neural activity when it looks at a vortex, when it doesn't. And you add that back to the model, like the exact same, like maybe these neurons are turned on, these neurons are turned off. You basically like apply that same state to the model for a different physical system. And this is the steering. You're steering the activations. So it's like you're adding this vector to the activations inside the model. It's basically like, oh, you saw this neuron was like pulsing when it was looking at a vortex. So now you like push that neuron to kind of like simulate a vortex internally. And it turns out like this works. So the concepts are kind of well described by just vectors, like linear vectors internally. So this is a vortex that we've fed into the model, and we've subtracted this delta vector. So we've subtracted it. And you can see it removes the vortex. Yeah?
The equation you showed in the slide before, is that something that you do during fine-tuning of the model? Like
Only during inference. This is all during inference when you've trained the model, and now you're just measuring the neurons. And then you're like, kind of like steering the neurons towards what you saw in terms of the activity. And you assume the simplest, like it's just linear directions. You assume, okay, it's basically like I'm assuming that the neurons are a linear combination of vectors corresponding to different physical concepts. Therefore, if I take the difference between the vectors for concept turned off, concept turned on, that should pull out that vector, is the hope. And so there's probably like other vectors kind of interfering, but it does work like surprisingly well. So you can kind of turn off the physics and then turn on the physics. So this is amplifying the vortex. Even though you've given it this laminar flow state, you can kind of alter it. So it's basically like you're poking the neurons, like, poking its brain to kind of like activate a certain type of physics. So one of the questions we get is like, okay, does the model actually understand that? Or is it just like, it's just like painting on a vortex, but it doesn't get it. Like it doesn't understand what it is. So the first thing you can do is look at the other physical fields. So that's density, pressure, velocity, velocity. And it actually does, like, it causes the right physics to generate a vortex. Like it doesn't just draw on a vortex on the density field. It actually like generates the correct state that has a vortex. The other thing is that because our model has been trained on many different physics, we can actually try to transfer this concept. So if we assume that this model, like internally in its brain, is representing like all vortices with the same neuron activity, like maybe we can just turn it on in other contexts. So we did that. This is a different PDE. It's still like a special case of Navier-Stokes, but it's very different conditions. This is with the vortex amplified. So it's like you basically poke the neurons that correspond to a vortex, and you see it starts generating all these eddies, like way more eddies than before. And then you suppress it. So you subtract that vector, and you see now there's like very few vortices, which is cool. So it seems like there's some transferability in this physical concept vector. The craziest thing is we thought, okay, like, what about a system that doesn't have a vortex at all? Like there's not even the concept of velocity in the system. So this is reaction diffusion system, which has two fields, like representing chemical species, but nothing else. There's no velocity field, no density field. And we tried amplifying the vortex, like just like pushing the neurons for a vortex, and you see it kind of generates like these swirly patterns in the chemical species, which is cool. Like it seems like it has this general notion of the physics. We tried this for other physical concepts. So this is diffusion. So like amplifying diffusion, you can see it kind of like, diffuse, like it's more diffusive. This is suppressing diffusion, so turning off diffusion. And you can see like it almost has like these numerical artifacts forming because there's no diffusion at all. And this is like, these are continuous concepts, so you can kind of scale it up and down. So this is like continually increasing the diffusion, decreasing. You can try with speed as well. So this is turning down the speed of the simulation, turning it up. The way you generate this data set is just by like downsampling in time. And then you've got one data set that's twice as fast. So that gives you this vector. This one kind of exploded, which is kind of interesting. It kind of looks like if you have a numerical simulation with too large a time step, you kind of get these weird artifacts. Okay, cool. So I guess so that was 2025, we released these foundation models. 2026, we're gonna start applying these to different topics. So one of these is this cool turbulence experiment. So this is in the basement of the applied math department. They have this giant fluids tank where they run turbulence experiments. And basically you get this particle, they have this dyed, in one of the, they basically have like a dense fluid on top of a light fluid, and you release it, and then you scan this laser across this fluids tank, and it measures the density of the fluid as a function of time and space. And you get this nice, so this is the data we get out of the experiment. And so the idea here is that real world turbulence is obviously like more accurate than simulation because it's the real world. So because our model is very good at low data training, we could in principle, train it on this experimental tabletop data set that our collaborators gave us. And then we'll have a model that kind of speaks the real world turbulence. So this is ongoing. Just kind of watch out for the paper. This is another cool paper. So this is led by one of our interns, Nolan. You can go to this link. I hope it still works. It's essentially a search engine for galaxies using natural language. It uses the embeddings of the ion foundation model. And so it's basically like they aligned the text embedding with the ion embedding. And so you can actually like type in like stream, and it'll like find stellar streams for you, which is pretty cool. You can also do like image search. So like you want to find similar galaxies to this, you can actually add that. So yeah. This is real data.
Okay.
Yeah. It should be live if you want to try it. Oh yeah, I'll just talk about it. So this is my research group. Some of them are involved in some of these projects. And then this is the polymathic team. So it's a kind of growing collaboration. And I guess to kind of conclude, I think foundation models are really exciting for science because they address this problem that we've had that machine learning doesn't generalize. I think they address it in a nice way, which is learning general representations from diverse data. And we might get some of the generalization properties of physics that way. And I will stop there. Thanks.
I'll kick off with one question really quick. So this tabletop experiment and other things like that. So there's obviously going to be less data available in this very controlled environment. Do you think just general videos that exist in the world would be a good way to teach physics, or do you think it's important to start with these specialized data sets?
Yeah, so one of the foundation models that used the well data set, and they actually released their foundation model before we did. It's called Physics X. And they basically took a video foundation model and they just did more training on the physics data sets. And it actually worked really well. I don't know if that would give you better performance because you might have the situation where you're doing a rollout and the density field just has a cat face up here or something. I don't know. I mean, yeah, but I think there's some things that you can learn. Some things you probably would maybe mess up the representation because in general videos you have unobserved things, whereas we all these data sets that we give it, they're fully observed. Yeah.
My question is to you as a representative of your generation. Don't you think that you're basically shooting yourself in the foot in the sense that, first of all, these models will replace postdoc students and we would lose those jobs available in the market. Secondly, we are getting results without physical understanding. We don't know why we're getting these results. So it's not really physics in the traditional sense of trying to understand something. Mm-hmm. And finally, we're actually producing models that would make us dumber in a way, because if you are getting used to the model giving you the answer, you're becoming lazy, you don't exercise your brain, and it's just like a muscle that you lose the capability of practicing in the future. So three issues that represent a threat for the future.
So, for us, these are physics foundation models. They're not like language models. They are kind of purpose-built. It's more so designed to replace existing pipelines where you're already using machine learning in science, and your model just doesn't generalize as well. Now, in the context of, I guess, like physics discovery. So actually, I didn't have time to talk about it, but a lot of my work is interpreting these models and trying to pull out the things they've learned. And I think this actually accelerates the discovery process because it gives us a different way to work with data than we currently have. I would argue that, in weather prediction, for example, there's this one simulation code that's like, I don't know, 1 million lines of Fortran, and nobody understands that code anyways. And so the weather model that people train from data is actually, in many ways, it's more interpretable than this colossal code with all these different heuristics physics added. Whereas the weather model is just directly trained from data, and it kind of, you can inspect the activation space and kind of get a physics understanding. So I think there's a trade-off. Definitely the objective here is to accelerate science, not to replace anyone. I think that's kind of how I've always viewed machine learning, is just I want science to go faster. And I think this is a really powerful alien tool that we're learning to use in a better way. And I think physics foundation models, I think they're actually going to give us more interpretation because they have these better representations than in traditional machine learning for science, where you're just interpolating data. I don't know if that answered. Yeah. What? Yeah.
You're not losing sleep.
No. I think it'll be great for science. Yeah. I mean, I think machine learning is both overused and underused in science. So overused, there's many contexts where you shouldn't be using machine learning, but people do. But I think there's other areas where they're not using machine learning, but they should. So I think there's both scenarios are happening right now. Yeah.
Hi. So I'm really excited about the result that pre-training gives you better performance. And that's great because you're eliminating a lot of waste, probably much better to the environment as well if you don't have to retrain every single model. But are you finding that if your initial set of data that the model's learning from isn't good, it isn't complete, like the pneumonia example, where it turns out all the images you're feeding of the false positives are just, they show the hospital ward in them.
Yeah.
Do you now just have bias that it's much harder to sort of decouple because you're training and retraining on different data sets? How can you, necessarily, would that necessarily make your bias a bit worse?
I mean, I think, I think there is, so I guess one of the assumptions that I think many scientists have is that an uninitialized model, like a model trained from scratch, is somehow a neutral prior. Yeah. This is not true. An uninitialized machine learning model is actually a very specific prior, and it's actually bad prior. It's not a good prior. And this is why even training on cat videos gives you better post-training performance than if you start from scratch. I think training a model from scratch is purposefully using a bad prior, a very mismatched prior, whereas pre-training on data, even if it's not completely relevant, is actually using a better match prior. So yeah, I don't know if that answers your question, but
yeah, I guess my question is, when it goes wrong and you find some issue, how do you know what caused it? If you're training.
We're doing pre-training. I mean, yeah, I mean, I think science foundation models are so new that we haven't really investigated these sorts of problems. Like in language, they have. Like there was one, I don't know if you've read this funny example. There was like one of the early, I think GPT-2 or GPT-3, there was this very specific, unusual word in the tokenizer. And it was because of someone on Reddit who was writing, prolific amounts of fan fiction. And it just ended up being like a big part of the pre-training data. And so their tokenizer literally had this person's username. And you could kind of use that person's username to jailbreak the model. So that's an example of like, your pre-training data, even if you post-train it a lot, the pre-training does still bias it in some ways. We haven't investigated that enough in our models to really understand that, but I think that's a really interesting, important question. Yeah.
So first of all, that was a great talk, and this is very exciting and ambitious. And by science standards, these models are huge. But of course, we in astronomy or science in general will never have a gigawatt data center, and the gap will grow between industry and academia. So my question is there a world in 2030 where like Sora 2030 can just take in your data and compute the PDEs and give you a better result because of scale?
Yeah, I mean, I think there is a world in which industry starts training on scientific data. I think it will still want open source models because there's so many examples where you need to do fine tuning because your data set has like some numerical artifact that you want to kind of marginalize out. If you're just using like some proprietary model, you could never do that. So I think you're always going to want open source models in a science foundation model context. Whether industry is nice enough to do that for us, I don't know. I would kind of lean towards maybe not, because they can't make money on it, unless it turns out that like training on spectra like makes their models genius. I don't know. So yeah, I think like if that happens, great. Like I think if there's open source models that industry has trained, that's amazing. I guess the other thing is that these models are too big for a single grad student to build, but I think at the same time, science has built large things before. Like the LHC is not something that a single PhD student is going to build for their thesis. It's large collaborations, and you work on a part of it, and you write your thesis on that. And I think that is kind of the maybe one direction we can go. It's just large collaborations with shared compute, much like shared telescopes.
So one of your key points is that the reason you build these models, and one of the reasons you think they're successful, is that they learn features that are physical. And you use a CNN to encode your data largely because it has some translational equivariance on images, right? Mm-hmm. So why not encode more symmetries and more physics into the model during the pre-training stage?
So some of the data violates those symmetries. So we don't want to bake those in. So for example, like some of the data is like data around a planet, and so the inertial forces kind of break the rotational symmetry. So there's a lot of symmetries that many of the data sets have exactly, but other data sets that the foundation model needs to process do not have it. Like some of them, they don't even have translational equivariance. So that's why we don't even have like exact translational invariance. We do give it like full positional encoding, so it can violate that. I guess that's the number one thing. And the second thing is like, I think there's an argument to be made for not giving the model certain symmetries at pre-training time because it can mess up the training dynamics. So for example, like AlphaFold 3 removed the translational equivariance that AlphaFold 2 had because it just hurt performance. And that could be like, it's better to teach someone by letting them figure out everything for themselves versus like giving them all the answers. I don't know. Like it seems to be like some combination of learning loss landscapes. Obviously, like it's a real symmetry. It exists. I don't know the right way to give it to the model. Like it's probably at the post-training stage.
All right, and one last quick question.
So when you train a model to like do arithmetic or maybe predict orbits, and it really learned the correct way to do it, you would expect that if you give it something out of distribution, like maybe a very weird orbit or a very weird addition, it would do so perfectly without any fine-tuning. Do you have any, like what would data out of distribution like this be, or any thoughts on this?
So I'm trying to think. I guess like in the Walrus paper, so we give it some examples that are out of distribution, like it's a Reynolds number that it hasn't seen, and then we test the model on that. Like it still falls off in performance, but it generalizes better than current machine learning models that are more specialized. But yeah, like physics is still like, you know, rigorous physics frameworks are still far superior. If you do know the physics, like often you don't, and that's where this kind of model can help. Like the turbulence example I showed, like that's an example where simulation fails. Yeah, and weather is another one.
All right, so Miles will be here the rest of the day and tomorrow if you still have questions, and let's thank him one more time.
Okay.